Hey guys, so as you all know from previous videos that I've done, I am absolutely head over heels in love with astronomy. Um, and this book I have actually realized is more lenient into a branch of astronomy known as cosmology. Cosmology is, of course, a branch of astronomy dealing with the sense of theories such as the birth of the universe, the death of the universe, and just overall the lifetime that happens before, during, and after the universe. And I find it absolutely fascinating. It deals with physics, it deals with so cosmology, for it to work, of course, deals with astrophysics, meaning like how does a star behave during certain pressures, like how, like inertia, think of it like that, like orbit and everything. Astrochemistry, meaning like what is the composition of a celestial body such as a star or a planet. Astro astronomy, of course, being the branch itself of science, the study of the universe and the cosmos. Everything like that. It deals with it takes a little bit of each one of those branches and blooms into one branch that is under the astronomy belt that essentially deals with, what I said, the lifetime of the universe. Like, because of how stars behave, it is likely that this will happen, stuff like that. So I'm strolling through this book by Brian Cox and Andrew Cohen. Wonders of the Universe. You can see the Horsehead Nebula right there, the stars, and how it's on the sci-fi channel and the science channel on TV. I think that's the Boomerang Nebula. But I'm going through and I see this page. It is absolutely beautiful. Let me try to cover the light up a little bit. It's absolutely stunning, I find it. Now, in the descriptions down here, I realized that some of these don't mention the names. Like this one mentions the name right here. And this one does not. This one does. Okay, yeah, these ones all. Okay, yeah, these all mention their names that I can see. I just want to admire how beautiful these look, really. I know I sound super high. I promise you I'm not on anything. I did just take some melatonin, which is making me kind of sleepy, but that's just about it. Look at that. Now, something I have actually heard is a mathematical term used in just about anything. Anything and everything. It is known as the golden ratio. The golden ratio is it's kind of hard to explain, especially the fact that I don't fully understand what it is. I know I do have an idea of what it is. It is some sort of equation that basically makes everything look perfect. Whether it be something as simple as a perfect shape, like a perfect spiral, such as this, or something as complex as the human face. Now, a lot of Renaissance painters have actually used the golden ratio to do details so minor that you would probably overlook in the entire painting, but it's actually one of the biggest, most important factors of the entire painting: the eyes. The eyes use the golden ratio because you don't want it to be too wide or too slant or not teardrop like enough, too teardroppy like, and too much of a circle, too much of an oval, stuff like that. They use what's called the they're the golden ratio, and they use that for the entire face. And something we have actually found that blew everybody's minds that has actually heard about this is the fact that the golden ratio is not only found in Renaissance paintings, but what, like I said earlier, is actually found in perfect spirals, such as this. Galaxies use the perfect golden ratio for, of course, whirlpool galaxies and whirlpool, so spiral galaxies, whirlpool galaxies, galaxies in the figure 8, the galaxies that are just kind of explosions from nebulas of dying stars and everything like that. Now, these are actually planetary nebulae, or nebulae, however you want to pronounce it. Meaning that all the light you see is from an explosion, from I want to say a supernova. And this one I think is my favorite. Out of the 8 of these, I think this one's my favorite just because I recognize it the most. And it was a tough tie between these, like this kind of triangle right here, since that one reminds me of a jellyfish, kind of. And that one is actually described to look like a cat's eye, almost like a cat glaring at you. But I think this one's my favorite. It just looks like a human eye, just kind of peeking at you through the darkness that is the rest of the space. Let's see what else is on here. Some of the astronomers. It's talking about the supernova. Now, it seems as though this is almost taking place as like a branch. It can either go into a black dwarf if it collapses on itself, but not enough to become a black hole, or it could be the second most dense thing in the entire universe, which are neutron stars. Neutron stars are so incredibly dense. For 1 tablespoon of its contents will weigh 100 million trillion tons, from what I've heard. And of course, nothing that we know of is more massive than a black hole, but a neutron star is a close second. And black dwarfs and the brown dwarfs, which it doesn't say here, but I'm pretty sure that's a brown dwarf, because a brown dwarf is basically a star that is either failed or a star that has completely died out, that wasn't dense enough to become a neutron or black hole or black dwarf, but rather just the core. It doesn't emit any light or heat, and it's too metallic and or not metallic, but it's not quite a planet either, because it has, I would assume, just a different composition, and it's too dense for it to be a star, or for it to be a planet. I'm pretty sure that's a brown dwarf. And a black dwarf and a brown dwarf, I forgot the difference, but I don't think either one emit any light. Neutron stars, they do emit light, and I believe some sort of heat, and I do believe they do emit very, very high concentrated bursts of gamma rays, which, if a neutron star is spinning, and it's spinning fast enough, then those gamma rays will almost look like it's pulsating, meaning you see it and then it's gone, and then it comes around, you see it and then it's gone, kind of like that. And that is a pulsar. A pulsar is a neutron star that is basically just spinning very, very quickly. A neutron star and a pulsar are basically the exact same thing that I know of. They could be different. If I am wrong, somebody please correct me on that. But that's just what I've heard. Now, technically, all stars, in a way, are pulsars, but they're not considered a pulsar, plainly because, one, they're probably not spinning fast enough, and two, they don't have enough concentrated beams of gamma radiation, of course, radiating out into space in the form of gamma rays and photons, because they do emit light, as you can see. Hence why the color is kind of white. Now this is a drawing, but you can see how it's still emitting light. It looks like it's fanning out, similar to the supergiant or this main sequence star. It's emitting light, and you can see on this one it is emitting no light. Hold on. There we go. It is emitting zero light, hence why it says the core stops glowing. And black holes, believe it or not, one of the brightest, I think either one of or the most bright object ever found in the known universe is actually a black hole, believe it or not. Ironic, isn't it? It's because of the secretion disk, or because of the disk of stardust and materials and magma and everything else just swirling around this one very deadly, very violent black hole. It is an active black hole. And I believe it's, if I'm not mistaken, it's a supermassive black hole in the center of a whirlpool galaxy, if I'm not mistaken. I could be wrong. I do not remember. Look it up real quick. Come on. There we go. There we go. You see all of these science tabs just bookmarked onto my ocean cleanup search engine. The brightest black hole. Monster black hole, largest and brightest ever found. And I believe it is, let's see, these are all artist presentations. None of these are actual photographs, of course. Well, except for this, but this is not the black hole that I'm thinking of. It's just M83. Or is M83 the blackest? There's a Sagittarius A. That's okay. Sagittarius A is at our Milky Way's galactic core, but it says it is the largest type of black holes, not the largest black hole. And there has actually been a question going around. Why is our black hole at the center of our Milky Way galaxy, Sagittarius A, so luminescent? Why is it flaring, and why is it so much brighter all of a sudden? And people have actually been guessing about the black hole actually swallowing a giant star, but nobody knows for certain because, well, wouldn't it mess with the gravitational balance of our Milky Way if the black hole did swallow something that bright to make it shine as bright as it did? Wouldn't whatever it was actually affect our Milky Way galaxy? I don't know. I'm no astronomer or scientist or anything. More cosmology. If you don't know what cosmology is, just keep thinking that to yourself and associate this title with the universe. This is a cosmology book, and I absolutely love it because astronomy is my favorite. And if I'm not mistaken, the periodic table is somewhere here, around here anyway. Planck Era, meaning the forces of nature, being the weak, the strong, which is gravity and everything else. All of those just kind of separating. Hold on. This absolutely blows my mind, how big this number is. The theoretical Big Bang is actually in trouble due to redshift and everything else. I don't exactly remember why the Big Bang is in such a little, like a tight little pickle, but and I don't know how it has that much relation to redshifting or the Doppler effect, but scientists have actually said that the Big Bang could be a fake theory. The theory could be proven wrong, but it hasn't yet with solid proof, so nobody knows. Planck Era. Planck being almost synonymous with the smallest something can be. Like Planck length being the shortest distance you can ever go without breaking the laws of physics, or Planck temperature being the hottest you can go without breaking the laws of physics and thermodynamics. Because the hotter something is, the more energy that wave has. The more energy that wave has, meaning the more compressed it becomes. The more compressed it becomes, meaning the wavelength from peak to peak or crest to crest is becoming shorter and shorter and shorter until eventually there is so much energy added to one wave where the Planck length is only, the wavelength is only Planck length across. And if you remember what I just said, Planck length is the shortest we can go without our laws of physics and understanding of thermodynamics and astrophysics breaking down. So if we add more energy, then that means that that little distance will become smaller and smaller and smaller. And we just don't know what happens after that, because we can't get the wavelength to get any smaller, because it's already the smallest it can be relative to our current understanding of physics and astrodynamics and thermodynamics and everything like that. Planck Era is what I'm guessing to be the shortest amount of time from the beginning of something that is still considered the beginning of that something. I would assume anyway. It is still technically not the beginning, but it is the closest we can get to zero that is still technically greater than zero. Because if you count to 1, congratulations, you already counted to infinity. Because 0 to 1 Yeah, I mean, that's one unit, but that unit can be divided infinitely. You take that in half, take that in half, you take that in half, take that in half, that in half, that in half. Therefore, and so on, until eventually you just cut it down in half or in fourths or whatever you want. You've just done that so much that you have reached Planck length, which is, of course, like I said, the smallest you can go, theoretically. Now, the explosion that is believed to have happened at during the Big Bang has been theorized to happen 10 to the negative 43 seconds after the Big Bang, after the explosion. I'm trying to find out. I believe that after the explosion of the Big Bang, not the single point exploding, that's my apologies. After the explosion of the Big Bang, 10 to the power of negative 43 seconds after it, the four fundamental forces of nature that we know has actually separated, which is gravity, electromagnetism, and superforce. Gravity being the strong and the weak. Almost. Gravity, I think, has been defined, or not defined, but almost described to be the weak one, like the weakest out of all four of these. Because so I am obviously on Earth. I am raising my hand. I am beating gravity. Now, the gravity paradox that I have heard is, if gravity is strong enough to keep me down, then how am I defying it? I am a weakling compared to the celestial body I am living on. Yet I am defying its rules. I am saying, you are not the boss of me anymore. I am doing what I want. And, you can do that with just about anything that you can pick up. Come on, book. Work with me. There we go. You can do that with anything. Hence why gravity has been called the weak force of the fundamental forces of nature. Now, I do believe that is just a theory from what I've heard. I do not know much about that matter, so I'm not going to talk too much about it and make myself look like an idiot. But, I just really love space, man. Space is awesome. And the fact how hydrogen is the most abundant element in the entire universe that we know of. How the second most is helium, and I believe the third most is silicon. If I'm not mistaken, it could be something else. Just the fact that hydrogen is like 75%, helium is like 23 or 24%. Everything else is like 1 to 2% or less of the entire universe. Just blows my mind. Well, see you guys later. Bye bye.